Okay, I'm running a few minutes late, so I apologize for that. Posting this link on Blackboard real quick. And then we will get started. I have decided to switch things up a little bit. Well, a lot. I think we are all a little overwhelmed by what's going on right now. This online learning has been, it's been a gigantic challenge, and not in a good way, in a very frustrating way. I know some people are working full-time jobs, some people are sick. I don't think any rational person right now is sitting here saying there's absolutely nothing to be afraid of, because we're all a little bit afraid. Not to say it's crushing for most people. Hopefully it's not, but it's enough that I think I think I need to do something to try to help out. And my something that I'm going to do is I am going to get rid of the last 2 reading assignments. You will have a homework assignment due next week and a project due at the end of the semester. I'm not going to give you any more lecture quizzes. I think that's what we need right now. We don't need to be sitting in a place where we're all stressed out all the time. I've been playing a lot of Animal Crossing because that has given me some little piece of happiness. Yes, I've been doing that instead of uploading your grades. No, I don't regret that. It's been needed for me to try to deal with the stress. There's just so much work. So, just to reiterate, you have 1 homework assignment due, and you have a written project due. I haven't posted the details for the written project yet. I'm planning on doing that today. I was going to try to figure out how to better the audio quality, but I went back to a previous setup. I don't know if I like this very much. I actually have my laptop sitting on some boxes on a chair. So once again, if the camera starts going crazy, just realize I lost a lot of money and I may not be able to email you for a while. Also, I have realized like I need to lean back, because otherwise, like, if I lean forward, the webcam is like my eyes are super dark. I feel like I'm hiding. You can't see me. So, yeah. Okay. I'm going to give you this lecture. I will not be giving you lectures per se anymore. I'm going to be talking through how to finish your project, and that's going to be for the remainder of the semester. We have 3 weeks left. 3 weeks from today is the last day of finals. And 3 weeks, I will expect you to catch up on your old homeworks, do the project, and that's it. Let's just be done with the semester. I pushed you very hard for most of the semester. I don't regret any of that. This should be a hard class. The digital circuits is important, and it's something that I feel like everybody should know. The computerized components, which was what our reading assignments were over, other types of components. If you're an electrical engineer, it may behoove you to read them over anyways. If you're not an electrical engineer, and you want to learn about computers, that may also be great. This is material you can get from other classes, and this is also material that you can pick up on your own if you really want to. Some of it's pretty easy to deal with. But I have the last bit of what I'm expecting is this chapter. I'm not going to be giving you a second test. I think that's, again, I think that just in the interest of trying to bring some sanity to all of this, I just think we need to cut our losses, move forward, go into summer, get out of the school year, and restart next semester. So that's where I'm standing. If you have any questions, please email me. I will continue to try to upload your grades when I have time. Hopefully this will give me some extra time where now I can upload your grades instead of just constantly dealing with friggin' technology, which has been the bane of my existence for the last few weeks. Okay. So today what we're going to talk about, last time the audio quality was terrible. Yes. Yes, it was. I don't have any idea if the audio quality is any better this time, but this isn't a setup that I've used before, and it worked the last time I did it. So I'm assuming it is going to work this time. Nobody's left me a comment and said, "This sucks," yet, but I'm waiting for it. The last time we talked about Carno maps, we talked about how to, I was hoping for that. Thank you, Walker. We talked about Carno maps. We talked about how to take a truth table, use a Carno map, and come up with an output logic system. Okay. Thank you, Nathan. That's also good news. That's what I'm aiming for here. I like the fact that you can hear me. It's the way these things should be. Okay. So last time, would you like me to go back over Carno maps because the audio was so bad on the last lecture? If that's the case, then I can push off the homework assignment that's due next week. Walker says he's good. Anybody else? Yay, nay? Okay, well, Walker says he's good, so that's really all we need. As long as Walker knows it, we're good. I had said that entirely as a joke. I don't know if it, they say that sarcasm doesn't show up over the internet. But whatever. Okay, so this time we're going to be talking about flip-flops. Okay. What is a flip-flop? Well, that's not. We'll try again. So this is a flip-flop. You wear it on your feet. No, this is not art class. Yes, that is a flip-flop. You know what? I changed my mind. You're going to have a test. It's going to be on flip-flops now. Most flip-flops have an energy-absorbing element. It's akin to a capacitor on an electrical system. You when you press, it absorbs the energy of you falling, and it converts it into material stress strain. That's related to just the compression of the material. So this is a flip-flop. What does this have to do with class? Well, this flip-flop has nothing to do with class. This flip-flop has much more to do with this class. This is a flip-flop. Less comfortable one. You step on this one, it might puncture your foot. So don't do that. That's not the purpose of this flip-flop. This flip-flop is for stepping on. Yeah, this flip-flop is made for walking. This flip-flop is not. It's made for flopping. What is a flip-flop? Well, if you did your reading assignments, which you should have done, a flip-flop is a method of storing information. Okay? We don't have a good way of storing information using the components I've given you. All right? If I take an AND gate, how do I store information on this? This gives me a real-time feed of whether or not both of these events are occurring simultaneously. This does not tell me what happened 1 second ago. This has no impact. 1 second ago does not impact this circuit. Okay? So how do we build a circuit that has memory, that can store something, that can take information and keep it? This doesn't do it. An OR gate doesn't do it. An inverter doesn't do it. I'm sure we could plug it. I can't tell you about a better way of doing it using the components we have yet. Instead, somebody's developed what's called a flip-flop. The purpose of a flip-flop is to store items. Let me give you kind of a yeah. Let me give you this. So here's an AND gate. Okay, I'm going to make it a NAND gate by putting the dot on it. I'm going to take it. It's going to go over here. Okay, and then I'm going to take this NAND gate and I'm going to have it go back this way and go into another NAND gate. Now this is the only input into a NAND gate. It basically makes it into an inverter. Okay. So now the only input into each of these NAND gates is the output of the other NAND gate. Okay. Why are we doing that? Well, here's the thing. In a NAND gate, here what we would probably do is maybe this would be a 2-input NAND gate. You would just take the same input, put it twice. What that does is that basically says, okay, I mean, if it is on or if it's not on, you're either going to get the 0, 0 or the 1, 1. There is no possibility of 1, 0 or 0, 1. There's only 2 options, 0 and 1. So your truth table looks like this. A, B, where A is your input, B is your output. A can either be 0 or 1. If A is 0 going into this, then B is 1. If A is 1, meaning this is on, B is 0, meaning this is off. Okay? So I'm going to label the outputs of this entire system as Q and Q naught. I'm going to label this wire right here A. This is B. B connects to the input of this NAND gate, which produces C. Okay? So just labeling convention now. You'll notice C is the same thing as A. You'll notice C is the same thing as Q. You'll notice B is the same thing as Q naught. Okay? So A equals C equals Q, and B equals Q naught. All right? This is the relationship between A and B. If A is 0, B is 1. If A is not 0, B is 0. Okay? So let's flip that around now. Look at the relationship between B and C. This is just an inverter. Using a Nand gate like this is just, I mean, I could replace that with an inverter very easily. It changes nothing about the system. Okay, we're going to call this 0 and 1 now. If B is 0, C is 1. If B is 1, C is 0. This is this table again. Now we also know that A, well, that's a little redundant. This becomes very cyclical. Okay, if B is 0, C is 1, C is 1, A is 1. If A is 1, B is 0. B is 0, C is 1. If B is 1, C is 0. If C is 0, A is 0. If A is 0, B is 1. If B is 1, C is 0. C is 0, A is 0. Again, very cyclical. Now, the way that we've drawn this right now, there is absolutely no way for us to change the system. We have no idea whether A is 0 or 1 right now. If we did know whether or not A is 0 or 1, we would be able to take this information and solve the entire rest of the circuit. And there is no way the rest of the circuit can change at all. This is a flip-flop. This is storing information. Okay, this could have easily been drawn as, instead of a NAND gate, an inverter. Okay, gives you the same effect. Probably should have drawn it as an inverter, but whatever. Same thing. This truth tables are the same, the inputs are the same, the outputs are the same, the entire system is the same. We're going to call this Q. We're going to call this Q prime. Okay? Usually Q prime and Q are opposites of each other. Q prime is like Q naught. Okay? This is storing information. Whatever this system's set at, whatever A is, A stays. And it stays that way forever. And we can't change that. And because A is a certain way, Q is a certain way because they're connected. Whatever A is, B is a certain way because it's the opposite of A, and which means Q prime is that. And then B is a certain way, which means C is a certain way, which means Q is that. It stays that way forever. This is a flip-flop. Okay, we've finally figured out storage by jankily connecting two components together. So this is not a good form of storage because we have no idea what any of the values are, and we cannot algorithmically determine them. They're indeterminate. A could be 0 or 1. We only have two options here, but we do not know which one. You've got a 50-50 chance. So let's take this flip-flop idea now. And now we're going to put it into a NAND gate, okay? Again, but just this time better. So I have two NAND gates. And this time, I'm going to have the output of this NAND gate go into the input of this NAND gate, and the output of this NAND gate go into the input of this NAND gate, okay? We'll go ahead and call this one A. I'll call this B. We'll call this C, and we'll call this D, and then this will once again be Q and Q prime. Okay, Q and Q prime are the ultimate outputs of the system. Usually in a flip-flop chip, Q and Q prime will be listed as a pin, and you can actually read those pin voltages. Okay. So now we've got two NAND gates. Well, all right. This poses a very interesting problem. We now have a very unique truth table that's going to come out of this, and I will explain why. In a NAND gate, if either input is on, if both inputs are on, okay, this is on unless both inputs are on. In that case, it's off. So for NAND, oh, I should have made these NOR gates. Dang, sorry. I'm gonna make them NOR gates. You make this out of NAND gates, but I want these to be NOR gates. I apologize. Okay, so another NOR gates. For a NOR table, if either input is on, the system is off. I think I'm looking for a NOR gate. Let me grab this quick. I might have been right with the NAND gate now that I'm questioning myself. No, I am looking for NOR gate. I'm right. Okay. I thought so. If either input is on, the NOR gate is off. Okay. Well, we've got this hooked up the same way that we hooked up the last flip-flop. Okay. We don't really know how the system starts. Again, we have no definitive way of proving this. If A and B come in at 0, we don't know what they are. They don't impact the system at all. So when it comes to developing our truth table, the way that you write a truth table for this is a little different. Okay? Let's say we've got, I'm going to call this S and R, which is what it's supposed to be called. This is R, this is S. Let's say I've got S, R, and Q. Okay? Q prime is just Q naught. If S comes in as 0 and R comes in as 0, this system behaves like the one that we just had, which is just an inverter. Okay? Whatever the system had when S and R came in, both being 0, it stays that way. Okay? So the way that that's written is Qn minus 1. What this means is that whatever state it was at the last clock cycle, is the same state. It hasn't changed. No change. If S and R are 0, no changes to the system. Nothing. Okay? The second thing that we can have is if S is 1 and R is 0, coming into this, if S is 1, remember, if either input is on, the NOR gate is off. So if S is 1, this forces D to be 0, which means Q naught is 0, which means D is the input into this system, 0 going in, R, oh, I've got that exactly backwards. S is 0 and R is 1. Okay, if R is 1, 1 going into this forces C to be 0, which means it forces Q to be 0, which means we know the answer right now. Q is 0, which means we have a 0 going into this. S is 0, Q is 0, which means D is 1, which means both R and D are 1. And it stores that state as long as S is 0. Okay, now we have the other state of S is equal to 1, R is equal to 0. If S is equal to 1, then this does the exact opposite. D is forced to be 0 because S is 1. Doesn't matter what C is. Does not matter. D has to be 0 because S is 1. D then being 0 goes in here, with R also being 0, means C is 1. Which means this comes back and both S and C are now 1. Q prime is 0, Q is 1. Okay, so if both of them are off, nothing changes. If S turns on, Q turns on. If S turns back off, Q stays on. S turns back on, Q stays on. S turns back off, Q stays on. Until R turns on, Q stays 1. As soon as R turns on, Q becomes 0. R turns off, Q is still 0. Okay. Now there is one more condition here. What if both S and R are on? If both S and R are on, and what that means is Q and Q prime are both 0. The way that this is written in the book is this is not an allowable configuration. While we can determine what Q and Q prime are, with S and R being on, typically you shouldn't do that. That's what it means by not allowed. Okay. But this is what this right here is called. This configuration is called an SR flip-flop. Okay. Yeah, there is no way I can cover all of flip-flops by Tuesday. But well, by today. We're going to be covering flip-flops again on Tuesday. Sorry, one last lecture. And I'm going to postpone your homework assignment due Tuesday for the week after. Again, no reading assignments. Additional to what we've already had. But this is an SR flip-flop. With this SR flip-flop, again, you've got a set state. Set state is what happens when S is 1. You've got a reset state, which is what happens when R is 1. Okay? If you set it, so if I were to draw a graph here, and this graph is going to be a graph of Q, and I've got 3 colors here. Okay, I've got Q, I've got R is going to be purple, and I've got S is going to be green. Okay? I don't know if any of those colors show up. And this is a plot versus time. Okay? Let's say that I have R and S as 0, but I have S hit 1, turn back off, turn back on, turn back off, turn back on, and turn back off. Okay? It's kind of like a clock cycle at this point. And a clock cycle, what it does is it periodically turns on and off at a very high speed. That's all a clock signal is. Okay? So this is my S, because it's green. Now I'm going to draw in my R. My R will also be 0 till here. Then it turns on, goes off, turns on, and goes off. Okay? Very quickly. I've got 2 spikes for my R. I've got 3 spikes for my green. Okay? What is Q? If we're giving it this input, if this is the input to our system, what does Q look like? Well, let's assume that Q starts out at 0. Let's say that right before this, R was set to 1 to reset the system. So we're coming in here, R is equal to 1, R drops down to 0 at 0, Q is 0. We have to make that assumption because otherwise we don't know what it starts at, and I have no idea how the beginning of this graph looks. Okay, so we're going to start out assuming that Q is equal to 0. As soon as S is equal to 1, Looking at this map, that forces Q to be 1. So Q goes up. Now, as soon as S drops off, and we now have both S and R equal to 0, which is right here, Q stays at what it was. So Q is currently at 1. Q is going to stay at 1. S turns back on. S turns back on, Q turns into 1. Q is already 1. That changes nothing. Q remains 1. Okay? S turns back off. Q remains at 1. R turns on. When R turns on, Q is forced to 0. So this goes back down to 0. R turns off. Well, when R turns off, we have 0, 0. Q stays at whatever it was. Q is currently at 0. Q stays at 0. Okay? Then S turns back on. When S turns on, Q turns on. S turns off. When S turns off, Q stays at whatever value it was. Okay, then R turns on. When R turns on, Q is forced to 0. R turns off. When R turns off, Q stays at whatever value it was. So I don't know if you can tell the difference between those 3 colored lines or not. I did my best to explain it. But Q is off, turns on, turns off as soon as R is set, turns back on as soon as S happens again, turns back off as soon as R is hit. Okay? In an SR flip-flop, the value of Q will turn on until the system is reset. That's it. I do believe a lot of computer memory is in SR memory. Don't quote me on that. But I do believe that SR is the type that's used in computer memory. It's very simple, not hard to build. You get this, it's either on or it's off. That's it. You go back and check the system, find out where Q is. While both of these are at 0, you can read its memory. That's what it takes. So this is one type of flip-flop, okay? The nice thing about this type of flip-flop is that it stores memory. It's very straightforward. You can determine its outcome based on what you have, okay? But this isn't the only type of flip-flop. This is just one type of flip-flop. The one that I gave you before with the inverters or the Nand gates, that's a different type of flip-flop. You can implement a flip-flop with Nand gates. They actually did that in the book. There's a different way of wiring the flip-flops as shown in the system. The next flip-flop that I wanted to tell you about, this one's also in the book, is called a clocked flip-flop. Okay? It takes the flip-flop idea that we've already developed and it turns it into something a little bit more controllable. Okay, and I'll explain again what the difference is here. Okay, we're going to start by bringing in an AND gate. Okay, 2 AND gates. Between these 2 AND gates is a clock signal. Clock is usually represented by the letter C in digital circuits. Okay, and then we're just going to add our S and R again. S, R. And then we're going to build the rest of the system the same way that we just built it. We got a NOR gate. We got a NOR gate. The output of this NOR gate. The output of this NOR gate. This one goes to Q. This one goes to Q prime. I think the book labels it Q prime. It actually labels it Q naught. Whatever. This one goes as an input into here. This is an AND, not an AND. This is an AND. This one comes back. feeds in here. This is a NOR, not an OR, a NOR. Okay, and then we've got this output here. So the way that this one looks is this is called a clocked SR flip-flop. Why is it called that? Because it's got a clock signal right here. What does the clock signal do? Well, in a clocked SR flip-flop, what we have is a little bit more control over the system. Okay. Your clock speed indicates how fast your computer system can calculate. Okay. It collects discrete data points at every clock cycle, and your clock cycle, the graph of the clock versus time, C versus T, as I said before, it just looks like this. It's a very periodic on-off. If you have a gigahertz processor, your gigahertz processor has 1 times 10 to the negative 9th seconds between your clock signals. That's what makes it a gigahertz. 2.4 gigahertz, it's 1 divided by 2.4 to the 9th power is the number of seconds between your clock cycles. Your clock cycles is just when your leading edge of your clock signal to the next leading edge of the clock signal. You know, it's kind of like a sine wave, except for this is a square wave. Okay, it's called a square wave because it only has 2 values, up and down. Okay, so this clock signal is very periodic, just on, off, on, off, on, off, on, off. But it gives very discrete times where we can actually measure things when it's on. And what it does here is, by putting this clock signal into these AND gates, means that this is only on when the clock is on. Meaning you only have the ability to change this system when the clock is on. It means that now Q comes in and it now has a value that is in sync with the clock. Your clock signal and your Q signal, the timing is going to match. That's important because otherwise you may have variability that's happening in S and R. You may have R and S rapidly jumping between 0 and 1. And if they're only allowed to change Q when the clock is on, then that variability is limited to only the times when the clock is on. Okay? So the truth table that comes out of this is we now have to add 2 pieces to it. Well, we now have to add the 1 piece to it, which is the clock. If the clock is 0, I don't care what these are, Q stays the same. Okay? The 2 minus signs in there, I guess the book uses an X. It means it doesn't matter. It does not matter what value those are. Q is going to be equal to whatever Q was before the system updated. Whatever the value was the last nanosecond is the value it is now. Okay? All of the rest of the situations have to occur where the clock is equal to 1. Because it's the only time when anything's going to change. There's no other situation where the clock is equal to 0 and something else happens. That's it. The clock is equal to 0, stays the same. Has to. Okay? So we only end up with 5 entries in our truth table, despite having 3 different inputs. It's just because we don't have to write out the other 3 inputs of what happens if clock is equal to 0. Because we're going to get this exact same answer every single time. So, yes, some truth tables are made nice that way. Okay, and here we have the same thing. If both of these are 0, Q stays the same. If S is 0, R is 1, Q is 0. If S is 1, R is 0, Q becomes 1. If both of these are 1, this is not allowed. Okay, once again, just not allowed. Okay, so this is a clocked SR flip-flop. We can take this concept, so as it goes in and out, up, down, up, down, up, down, up, down. If S or R flips and turns on in the middle of this clock cycle, one of them turns on, that will be recorded. If they turn on outside of the clock cycle, it doesn't matter. It affects the system none. Okay, we'll talk about the next type of flip-flop. The next type of flip-flop is called, that the book mentioned, is called an edge-triggered D flip-flop. Okay. Now, I just mentioned something that what happens when you've got S and R and they jump very wildly inside of one clock cycle. Okay, if they're jumping wildly between 0 and 1, you're going to have significant changes and then period where it stays the same, and then significant changes and period where it stays the same. This can pose some issues in where clock cycling isn't quite sufficient because it is rapidly changing on and off inside of a clock cycle. And if your clock cycle isn't set to the maximum speed of the computer, it just makes it harder. An edge-triggered D flip-flop takes this and it says, okay, this value is on, this value is off, but we have these two change periods here. We're going to call these edges. Okay? And what edges are transitions. It's where a digital signal changes between on and off. Okay? So if I'm looking at a signal and I got this for my signal, it's just one piece of a square wave. This here is called the leading edge. And this here is called the trailing edge. And if we know what those edges are, we can then take an edge-triggered flip-flop, which means that it looks for one of these edges to make a change. It stays constant if this is constant. It stays constant if this is constant, and it only changes if a change occurs. If a leading edge is detected, meaning it switches, or a trailing edge is detected, meaning it switches the other way. Okay, we're going to talk more about the edge-triggered D flip-flop and about JK flip-flops, which is the most fun term to use in all of electronics. JK flip-flop, JK. We're going to be talking about that on Tuesday. Again, your homework assignment will be due. I'll just make it due the next Tuesday. I'm canceling your reading assignments. No tests for the rest of the semester. You will still have your project due. I will post the details on that online. As soon as we finish talking about flip-flops, we're going to go straight into discussing how to do the project, and that will be the rest of the semester for this class. Okay? Have a good day, and I hope the weather's nice where you are, because it's kind of dark where I am. And it's not just because the lighting in my office is really bad. I don't have any windows. Hi.